Okay, welcome back everyone to this tutorial series on theory of computation. In this video, we'll be discussing a bit of the ramifications and uses of the closure properties that we've been discussing. So now that we've shown that regular languages are closed under, namely, the union, the concatenation, the star operation, and the complementation, okay, under these operations, what can we actually do with these results? So it turns out that these closure properties are actually quite handy to show that more complex languages are regular, okay? And so that's part of the motivation that I had used to introduce this topic. And so that's what we're actually going to be doing in this video, right? So like I said, we can prove that a language is regular, of course, by creating some FAM that accepts it. But what if L is made up of many pieces, right? So what if L clearly looks like the union of two languages, and then one of those languages is the concatenation of two other sublanguages? Then we might not actually need to go through the trouble of constructing a whole FA for this language. And in that case, we can just use the closure properties to show that this language is regular, okay? And that's what we're going to be doing in the following exercises, is using the closure properties to show that languages are regular without actually having to build any FAs, right? Okay, so the first example of this application of closure properties is actually going to be on a more abstract uh, um, idea, which is we're going to use the closure properties to prove another closure property. Okay, so in this case, we have two regular languages, and we want to prove that the intersection of these regular languages is also regular. So what we're doing is we want to use closure properties to prove another closure property, right? In this case, the closure property is the intersection. So in this case, if we're able to show this result, then we'll have shown that regular languages are closed under the intersection, okay? So the one thing that I want to make sure, though, is I want you to be aware that this is not always possible, okay? So meaning that there are some closure properties, so there are some operations that we know regular languages are closed under, but we can't directly use other closure properties to prove that. So for instance, if I go back a bit and I go to this example where we prove that that regular languages are closed under the reversal operator, we cannot do this by using other closure properties. And in this case, we had to use a construction proof, okay? But it turns out that in this case, we can actually use the closure properties that we've seen already to prove that the language L1 intersect L2 will also be regular. And so how do we actually do that? Well, we're going to use a nifty trick, okay, that actually requires you to recall De Morgan's law. So De Morgan's law for sets states two things. So there's two versions. It states that if you have a set A intersect a set B, and you take the complement, then you get A complement union B complement, okay? And there's another result that says that if you have A union B and you apply the complement, then you get A complement intersect B complement, okay? So the nifty trick is to actually recognize that you can obtain the intersection, right? So you can obtain the intersection. So you need to notice that L1 intersect L2 can be obtained by a double negation and an application of De Morgan's law. By a double, in fact, it's a double complement plus De Morgan's law. So what I mean by that is, suppose I have L1 complement union L2 complement, okay? And now, suppose that I apply the complement to these two sets. So if I apply the complement, then what I get is I get L1 complement intersect L2 complement. So from here to here, I've just applied De Morgan's law. The next thing I need to do is I need to notice that if I have L complement, then this is the same as L. Because if I take the complement of L, so I'm taking everything that's not an L, and then I apply the complement in L, and I apply the complement again, then I take what's not in L. So I get back what's actually in L, right? So L1 complement is going to be L1, and L2 complement is going to be L2. And so I get that the complement of L1 complement union L2 complement is equal to L1 intersect L2. But now, because L1 and L2 are regular, I know that L1 complement and L2 complement are regular, okay? Because regular languages are closed under the complement, right? And that means that L1 complement union L2 complement is regular because regular languages are closed under the union, right? Here is because they're closed under the complement, okay? And then if I take this language here and I apply the complement, because I know that this language is regular, once I apply the complement to it, I get another regular language. So L1 complement union L2 complement, whole complement is regular again because regular languages are closed under the complement. But then I just showed by De Morgan's law, this is L1 intersect L2, right? And so this is the same language as this. But I know that this language is regular because this language is exactly this language. Then L1 intersect L2 is also regular. And so because I started with two arbitrary regular languages, I've actually proved that for any pair of regular languages, when I take the intersection, that language will also be regular, okay? And so this is what I mean by, in number 2 here, identifying the sub-languages and language operations that make up L, and then using closure properties to prove that L is regular, right? So I identified in this case that I could rewrite L1 intersect L2 as this more complicated looking language, but that turned out to be exactly equal to the intersection, okay? And then I used the properties of the closure properties. I used the closure properties then, and the fact that regular languages are closed under the union and the complement to show that this language was also regular, Okay, and so just a note is that a proof by construction is also possible. I actually give part of a solution in a previous video when I'm constructing a DFA for the intersection of two languages. But I encourage you to think about what the construction proof, or at least what the construction would look like. And so a hint, if you want to actually try the construction, hint for the construction, is that in this case, you'll need to take the set of states of Q prime as the cross product of Q1 and Q2. So that's the hint that I will give you. Okay, and so this illustrates how to use the closure properties to prove that a language is regular. In this case, we've actually proved a whole new closure property.